Hello students. Today we are going to discuss about Unit 10, Water and Soil Quality Management. This is from MSc, second year. Now, what are the objectives of this chapter? In this unit, we shall discuss the water and soil quality management for aquaculture ponds and coastal system. It provides ideal values for various physico-chemical parameters important for aquaculture, including temperature, salinity, dissolved oxygen, pH, alkalinity, hardness, and nitrogenous compounds. Maintaining optimum levels of these water quality parameters is essential for fish growth and health. This also describes methods for monitoring parameters like turbidity, transparency, and controlling imbalances in the system. Also describes various kinds of aquatic pollution and causes of pollution, measures to prevent pollution, and methods of dilution of polluted waters. Now let us see what is water quality management. Water temperature, it is a physical property of water which expresses how hot or cold the water is. Air and water temperature is directly depends upon the radiation. Solar temperature can alter the physical and chemical properties of water. So the key to the successful culture of aquatic organisms is maintenance of water quality. So obviously poor water quality will be the poor harvest. So in water, light energy is absorbed exponentially with depth, and so most heat is absorbed within upper layers of water by dissolving organic matter and particulate matter. Water temperature influences density of water. Water temperature affects the metabolism, growth, and reproduction in aquatic animals. Many animals use temperature as a signal for when to reproduce and when to migrate. Generally, animals and plants grow faster at warmer temperatures, although all organisms have an upper temperature limit. Congenial species are to be selected for aquaculture as per temperature preference for maximum growth rate. Temperature measurement of water samples collected should be done immediately using mercury or digital temperature thermometer by immersing the calibrated thermometer into the water. The atmospheric temperature is also measured in a well ventilated area and in the shade at 1.2 to 1.5 meters above the ground using a 50 degrees centigrade calibrated thermometer. Now, what is turbidity? Water turbidity in freshwater ponds is caused by phytoplankton and zooplankton. These are the microscopic plants and animals. And suspended solids such as clay and silt particles in the water column. Now, water turbidity is important as it determines the amount of light penetration that occurs in the water column of a pond. This in turn will have an effect on the temperature of the water and the amount of vegetation and algae that will grow in the pond itself. For example, a highly turbid pond will allow less light penetration. Therefore, the temperature of the water will be lower. A combination of less sunlight and lower temperatures will result in a decreased amount of vegetation present within the ponds, which depend on sunlight and warmth to grow. A low turbid pond will of course have the opposite effect. Now, how to measure this turbidity? Turbidity is measured in centimeters using a Secchi disc, which consists of a round plate divided into alternate black and white pie sections. This disc is attached to a graduated rope or a metal handle divided into measuring units, usually at 2 centimeter intervals. The disc is lowered into the water until it cannot be seen and then raised until it reappears. These Sechi depths between 20 centimeters and 60 centimeters are recommended for optimal management of freshwater ponds. Now, what is salinity? The term salinity refers to the total concentration of all dissolved ions in the water, not just the concentration of sodium chloride in the water. Measurements of salinity is referred to as parts per thousand ppt. For a point of reference, seawater is approximately 35 grams per liter or 35 ppt. Each species has an optimal salinity range. This range allows the fish to efficiently regulate their internal body fluid composition of ions and water. So, how to measure this salinity? Using refractometer for in situ measurement. Open the daylight plate and apply 1 or 2 drops of the water sample to surface of the prism using a glass rod. Hold the prism at an angle close to parallel with the floor so that the sample will not run off. Softly close the daylight plate. The sample should make a thin film over the entire surface of the prism. No bubbles should be there. Look through the eyepiece. Focus the scale until it is sharp to your eyes by gently turning the eyepiece either clockwise or counterclockwise. So this is the table that shows the salinity levels of the water. So there are about 61 elements in. For more information, you can see the table here. Phosphorus and nitrogen are important elements that vary considerably in concentration due to their association with biological processes. Let us see how important is the oxygen. Oxygen is also lost from the system via respiration, where oxygen is consumed by aquatic organisms, both plants and animals, and by decaying organic matter on the pond floor. Declining oxygen levels can be caused by a number of factors. This includes large blooms of phytoplankton and zooplankton, high stocking rates, excessive turbidity that will limit the amount of photosynthesis occurring, and high water temperatures also. Levels of dissolved oxygen will also decrease after a series of warm, cloudy, windless days. Low dissolved oxygen can be lethal to our aquaculture species. Some effects include stress, increased susceptibility to disease, poor feed conversion efficiency, poor growth and even death. There are a number of ways to improve low oxygen levels, and there are different types of aeration systems that help circulate and oxygenate the water. For example, airlift pumps, paddle wheels, aspirator pumps, diffused air systems, etc. Flushing ponds with fresh water and reducing feeding rates will also help increase oxygen levels within the ponds. When taking measurements of dissolved oxygen within an aquaculture ponds, it is important to note that readings will alter depending on the time of the day, the amount of plant growth within the pond, the position in the pond from where the measurement was taken. This is due to the following reasons. Aquatic plants, algae, or phytoplankton are present in large numbers, will produce high oxygen levels during the day due to photosynthesis. However, at night, these organisms consume oxygen rather than producing via photosynthesis, so which may result in dangerously low oxygen levels. Therefore, if the pond has extremely high oxygen levels during the day, there may be a good chance they will drop considerably at night. So, as mentioned before, for dissolved oxygen analysis, the samples need to be fixed by adding Wrinkler's reagent or Bode vessel to the then surface and bottom water samples are to be collected separately for the near shore and offshore. The processing protocol should be meticulously followed for individual samples. The commonly used method of estimation of dissolved oxygen is by Wrinkler titration method. In this methodology, the oxidation of manganese dioxide by the oxygen dissolved in the sample results in the formation of a tetravalent compound. When the water containing the tetravalent compound is acidified, free iodine is liberated from the oxidation of potassium iodide. The free iodine is chemically equivalent to the amount of dissolved oxygen present in the sample and is determined by titration with a standard solution of sodium thiosulfate. Next, regarding the pH. The pH is the measurement of the hydrogen ion concentration in soil or water. The pH scale ranged from 0 to 14 with a pH of 7 being neutral. A pH below 7 is acidic and pH above 7 is basic. An optimal pH range is between 6.5 and 9. However, this will alter slightly depending on the culture species. An optimal pH range is between 6.5 and 9. However, this will alter slightly depending on the culture species. The pH is not dependent on other water quality parameters such as carbon dioxide, alkalinity, and hardness. It can be toxic in itself at a certain level and also known to influence the toxicity as well of hydrogen sulfide, cyanides, heavy metals, and ammonia. pH will vary depending on a number of factors. pH levels of the pond water will change depending on the aquatic life within the pond. Carbon dioxide produced by aquatic organisms when they respire has an acidic reaction in the water. The pH in ponds will rise during the day as phytoplankton and other aquatic plants remove CO2 from the water during photosynthesis. The pH decreases at night because of the respiration and production of CO2 by all organisms. The fluctuation of pH levels will depend on algae levels within the pond. Now, the problems with pH. Suboptimal pH has a number of negative effects on fish and microbrachium. It can cause stress, increase susceptibility to disease, low production levels, and poor growth. Signs of suboptimal pH include increased mucus on the gill surfaces of fish, damage to the islands, abnormal swimming behavior, fin damage, poor phytoplankton and zooplankton growth. It can even cause death. In the case of microbrachium, low pH levels will cause the shell to become soft. This is due to the shell of the crayfish being composed of calcium carbonate which reacts with acid. Now, how to control the pH? Treatment methods will depend on whether there is a high pH problem or low pH problem. To treat a pond with low pH, a pond can be limed with agricultural lime, fertilized to promote plant growth. To decrease a high pH, the pond can be flushed with fresh water. Feeding rates can be reduced to decrease nutrient input into the pond. Gypsum can be added to increase the calcium concentration. Alum can be added in extreme cases. So liming the soil is most essential to maintain the pH of water. As we are talking about it, the water should be slightly alkaline because the fish food organisms develop well at pH 7.5 to 8.5. So application of lime to the pond bottom help to eradicate the pathogens and parasites as well as to help maintain hygienic conditions. Lime materials like agricultural lime, quicklime, and dolomite also, these are commonly used along with this gypsum and alum. So the quality of lime to be applied depends on the pH of the soil. Next, carbon dioxide. The level of carbon dioxide in the water varies with the respiratory and photosynthetic activity of animals and plants in the water body. The level of decomposition of organic material in that water, a significant supplier of CO2 in nutrient rich waters, and the respiration of the fish themselves. Concentration of CO2 can rise to considerably high levels in systems with large number of fish and comparatively slow water turnover. How to measure CO2? Free CO2 in natural water is determined by titration with sodium carbonate, that is Na2CO3, to form NaHCO3. Development of pink color using phenolphthalein indicator in the natural water shows the absence of CO2 in the sample. The water sample is collected without allowance for bubbles in a DO bottle and is slightly closed. In the laboratory, an amount of 50 ml of this sample water is transferred to a conical flask carefully without bubbling, and 2 to 3 drops of phenolphthalein is added. If the water turns to pink, then there is no free CO2 in water sample. If the sample remains colorless, it is titrated with standard NO2CO3 solution. The end point is the permanent appearance of the pink color. The favorable range of CO2 in water is less than 5 mg per liter. So fishes are known to avoid CO2 concentration as low as 5 mg per liter. Lethal effects of CO2 normally occur at levels greater than 50 mg per liter. Sublethal effects have been recorded at 12 mg per liter of free CO2. High concentration of CO2 reduces the capacity of blood to transport oxygen. Fish can tolerate high levels of CO2 if dissolved oxygen is also high. So calcium oxide at the rate of 0.64 mg per liter or calcium hydroxide at 0.84 mg per liter can be applied to remove 1 mg of liter per liter of CO2 from tanks or other containers in hatcheries. It is seldom practical to remove CO2 from pond water. Now, water alkalinity and hardness. Alkalinity refers to the amount of carbonates and bicarbonates in the water. Water hardness refers to the concentration of calcium and magnesium. As calcium and magnesium bond with carbonates and bicarbonates, alkalinity and water hardness are closely interrelated and produce similar measured levels. Waters are often categorized according to degrees of hardness as follows. So if it is 0 to 75 mg per liter, it is considered as soft water. 75 to 150, moderately hard. 150 to 300 mg per liter, it is hard. And over or above 300 mg per liter, the water is considered as hard water. Alkalinity and hardness level should be maintained around 50 to 300 mg per liter, which provides a good buffering effect to pH swings that occur in ponds. A lack of calcium in the water will also result in soft-shelled microbrachium as they rely on the intake of calcium from the water column to harden their shells after molting. Water alkalinity and hardness can be increased by liming ponds, which involves adding a measured amount of lime to the pond. However, there is no practical way of decreasing alkalinity and hardness when they are above desired levels. So, the total alkalinity represents the quantity of basic anions present in water, that is, bicarbonates, carbonates, phosphates, hydroxides, etc. Alkalinity measures the total amount of base present in water and indicates the ability of a water body to resist large changes in pH. In other words, alkalinity shows the buffering capacity of the water body. So it is expressed as mg per liter CaCO3. The total alkalinity concentration should not be lower than 20 mg per liter CaCO3 in production ponds. The desired total alkalinity level for most aquaculture species lies between 50 to 150 mg per liter CaCO3. So it can be estimated by titrating the water sample with strong H2SO4, first to pH 8.3 using phenolphthalein as indicator, and then further to pH between 4.2 to 2 and 5.4 with methyl orange. Next is ammonia. Ammonia in ponds is produced from the decomposition of organic waste, resulting in the breakdown of decaying organic matter such as algae, plants, animals, and uneaten food. Ammonia is also produced by fish and macrobrachium as an excretory product. Ammonia is present in two forms in water, as a gas NH3 or as the ammonium ion, that is NH4+. Ammonia is toxic to culture animals in the gaseous form and can cause gill irritation and respiratory problems. Ammonia levels will depend on the temperature of the pond's water and its pH. For example, at a higher temperature and pH, a greater number of ammonium ions are converted into ammonia gas, thus causes an increase in toxic ammonia levels with the freshwater pond. So ammonia is nothing but the primary nitrogen waste. It's a byproduct of bacterial degradation. Lack of this might have a new tank syndrome. Two forms of ammonia in water depend on pH, temperature, and salinity. The acute toxic level in freshwater aquarium is from 0.2 to 0.5 ppm of unionized ammonia. Chronic toxic begins at 0.002 ppm of unionized ammonia. How to prevent? The prevention is by good animal husbandry, regular monitoring of water quality, limit overcrowding and overfeeding. If high levels of ammonia are present within the pond's water, a number of measures can be taken, which includes reduce or stop feeding, flush the pond with fresh water, reduce the stocking density, aerate the pond. In emergencies, reduce the pH level, control plant and algal growth, then add nitrifying bacteria. Aquatic autotrophs rapidly utilize ammonium ions, thus naturally preventing it from increasing to toxic levels. The total ammonical content of water is an index of the degree of pollution. Its concentration in unpolluted water should never be more than 0.1 mg per liter. The tan in water is measured making use of a spectrophotometer using phenol hypochlorite method. In this method, phenol and hypochlorite react in an alkyl solution to form phenylquinone monoamine, which in turn react with ammonia to form indophenol. Indophenol gives the solution a blue color, the intensity of which is proportional to the concentration of ammonia present in the sample. Sodium nitroprusside is added to intensify the blue color. Both ammonia and ammonium are measured because in a strong alkaline solution, all the ammonium is converted to ammonia. This procedure gives an estimate of total ammonia nitrogen. Then nitrite. So nitrite is, it originates as intermediary product of nitrification of ammonical N, that is ammonical nitrogen. The concentration of nitrite in water should not exceed 0.5 mg per liter. Nitrite is toxic to fish and shrimp because it forms methemoglobin, which affects immunity and circulatory system and reduces the transfer of oxygen to cells. High chloride concentration reduces nitrite toxicity, and so nitrate toxicity is less in brackish water. To measure nitrate, the nitrate in water is allowed to react with sulfanilamide in an acid solution. The resulting diazo compound further reacts with NNED and forms a highly colored ozo dye, the absorbance of which is measured spectrophotometrically. This chronic effect, if compared to ammonia, more toxic than nitrate, actively transported across the gill epithelium. Toxic effects of nitrite, gill hypertrophy, hyperplasia, hemorrhages, and necrotic lesions in the thymus. Increasing susceptibility to infectious diseases, short life of RBC also we can see. In hatcheries, nitrate can be controlled by installing biological filters and addition of chloride as sodium chloride and calcium. Effective removal of organic waste, adequate aeration, and proper use of fertilizers are the methods to prevent the accumulation of nitrite to toxic level in pond culture. So treatment success depends on the severity and duration of toxicity. Chlorine ions competition inhibit nitrite absorption over the gill. Partial water changes every 2 to 3 days. Clinical sign will often resolve in 24 hours. Then we need to increase the aeration. Keep checking the biological filters also. So as we learned that when nitrite is absorbed by fish, it reacts with hemoglobin to form methemoglobin. So since methemoglobin is not effective as an organic oxygen carrier, continued absorption of nitric can lead to hypoxia and death also. So the blood containing high level of methemoglobin is brown. Thus, nitrite poisoning is often referred as brown blood disease. Nitrite toxicity increases with increase in pH. It decreases with increase in calcium and chloride concentration also. So hence nitrite is more toxic in fresh water than in seawater. So recommended safe levels of nitrite in water is, as we discussed, it should be 0.3 mg per liter. Then coming to nitrate. It is the end product of nitrification of ammoniacal nitrogen by aerobic autotrophs. The favorable range of nitrate in culture waters is 0.1 mg per liter to 4.5 mg per liter. Its higher concentration may lead to inability to swim, and reduced movement. The estimation of nitrate in water is based on a method of reduction of nitrate to nitrite and then estimating the nitrate through spectrophotometrically. Nitrate in water is reduced almost quantitatively to nitrite when the sample is passed through a column containing cadmium fillings coated with metallic copper. Nitrate, it is non-toxic to fish, substrate for protein synthesis of plant and phytoplankton, absence of regular partial water change. High level of nitrate will inhibit bacteria oxidation of nitrite to nitrate. Nitrate level will start to increase. Nitrobacter, that is low activity in low temperature water. Eggs and fry are more sensitive than adults. It should be maintained between or below 50 and 100 ppm. High levels may encourage algal bloom and eradicate a vegetable to eradicate a vegetable filter or water exchange should be done. Next, phosphorus. So phosphorus is found in the form of inorganic and organic phosphates, that is PO4, in natural waters. Inorganic phosphates include orthophosphate and polyphosphate, while organic forms are those organically bound phosphates. Phosphorus is a limiting nutrient needed for the growth of all plants, aquatic plants and algae alike. However, excess concentrations, especially in rivers and lakes, can result to algal blooms. Phosphates are not toxic to people or animals unless they are present in very high levels. Digestive problems could occur from extremely high levels of phosphates. Among the common sources of phosphorus are wastewater and septic effluents, detergents, fertilizers, soil runoff, where as phosphorus bound in the soil will be released, phosphate mining, industrial discharges, and synthetic materials, which contain organophosphates such as insecticides. Phosphorus concentration is measured either by using total phosphorus, which is a measure to all the various forms of phosphorus that are found in a water sample, or by soluble reactive phosphorus, which measures organophosphate, the soluble and inorganic form of phosphorus, which is directly taken up by the plants. Dissolved inorganic phosphorus. Phosphorus is a limiting nutrient needed for the growth of aquatic plants and algae alike. So excess concentration of phosphorus can result in algal blooms. An algal bloom is a rapid increase in the population of algae in an aquatic system that can occur in green, yellow, or brown or red in color. Algal bloom is caused by an imbalance of nutrients in an aquatic system. For coastal waters, the dissolved inorganic phosphorus should not exceed 0.05 mg per liter and dissolved inorganic nitrogen should not exceed 0.5 mg per liter. Harmful algal blooms causes negative impacts to aquatic organisms via production of natural toxins, mechanical damage, etc. Dissolved orthophosphate can be determined by ascorbic acid method. Ammonium molybdate and potassium antimony tartrate react in an acid medium with dilute solutions of orthophosphate to form phosphomolybdic acid that is reduced to the intensely colored molybdenum blue by ascorbic acid. The intensity of the blue color increases in proportion to the amount of phosphorus present and can be measured spectrophotometrically. In pond bottom, decomposition of organic matter produces an acidic and reducing conditions. Thus, it is possible that liming may be useful even in the case of slightly alkaline soils, showing buffer action, resisting the increase of pH by lime treatment. If it can hold more of the inorganically bound phosphates as calcium bound phosphate, even without increasing the soil pH. What are the nutrient levels? Nutrients levels refer to the amount of phosphorus and nitrogen that is present in the water column. Nutrients are important as they promote healthy plankton blooms, which are necessary to maintain turbidity levels and provide feed for fish. Nutrient levels can be increased in the ponds by adding inorganic or organic fertilizers in measured doses. Increased levels of nutrients can be harmful. It can cause excessive plankton growth, potential blue-green algae blooms, and oxygen depletion. High levels of nutrients can be caused by high stocking densities, overfeeding, high productivity, and dead plant and animal matter. To increase high nutrient levels, feeding rate should be decreased, and the pond may need to be flushed with clean water. Total solids refer to any matter either suspended or dissolved in water. Everything that retained by a filter is considered a suspended solid, while those that pass through the are classified as dissolved solids, that is usually 0.45 micron in size. And then concentrations in water are both measured as total suspended solids and total dissolved solid respectively. Suspended solids can come from silt, decaying plant and animals, industrial wastes, sewage, etc. They have particular relevance for organisms that are dependent on solar radiation and those whose life forms are sensitive to deposition. High concentrations have several negative effects, decreasing the amount of light that can penetrate the water, thereby slowing photosynthesis, which in turn can lower the production of dissolved oxygen. High absorption of heat from sunlight, thus increasing the temperature, which can result to lower oxygen levels. Low visibility, which will affect the fish's ability to hunt for food. It clogs fish's gills, prevents development of egg and larvae. It can also be an indicator of higher concentration of bacteria, nutrients, and pollutants in the water. And there are other some micronutrients also, calcium and magnesium. The function of calcium and magnesium are quite similar in carbon dioxide mechanism of water. Relatively, calcium is more important. It acts to increase the availability of other ions and in general ameliorates chemical condition in the environment. It is also an integral part of the plant tissues. Calcium is generally present in the soil as calcium carbonate. Both carbohydrates and CN ratio play an important role in nitrogen fixation. Directly and indirectly, calcium, phosphorus, nitrogen, and other nutrient cycles depend mainly on carbon cycle. So, as the accumulation and decomposition of organic matter form an important study in the pond productivity. The role played by humus compounds in ponds is not clearly explained, though it seems that the exchange process between the nutrients absorbed on humus and the plant organisms is of great significance. Other than this, there are other micronutrients also. In addition to the major nutrient elements, some important trace elements, or as we call them as microelements, examples manganese, copper, iron, boron, etc., should be included in the soil study of ponds. Among the trace elements, probably manganese has been more extensively studied, but all these studies relate mostly to its role as an essential micronutrient for the growth of plant and animals. Now let us discuss about few diseases that are caused by the environment. These are, we can call them as environmental diseases that affects the aquatic systems. The first one is, we can say, gas bubble disease. It is caused by supersaturation of water with dissolved gases. Although oxygen and carbon dioxide can contribute to supersaturation, the predominant gas contributing to the problem is usually nitrogen. Gas bubble disease can result in acute, catastrophic, or chronic mortality. It may occur transiently and can be difficult to confirm. Supersaturation should be considered when unexplained mortality is encountered in an aquarium setting. One common source of supersaturation is the use of well water that contains high concentrations of nitrogen gas or CO2. This problem is easily remedied by aerating the water before it comes into contact with the fish. Now, the common causes of gas bubble disease in public aquarium includes the use of cavitating pumps, leaks in plumbing on the intake side, sometimes excessive turbulence in cold water exhibits. In these cases, the supersaturation is caused by atmospheric nitrogen gas. It is manifested by exophthalmos and the presence of tiny gas emboli within fins, corneas, or other tissues. The presence of gas emboli within the gill capillaries is diagnostic. Then, nitrogenous compounds as a cause of environmental diseases in aquatic systems. New tank syndrome. It occurs when NH3 levels rise during the first 2 to 3 weeks after a new system is set up, or when NO2 levels rise subsequently because the microbial population of the biofilter has not had time to develop. In this situation, the ammonia or NO2 concentration will be increased. However, all other parameters should be within normal limits. Beginning aquaries are likely to overstock and overfeed new systems, resulting in significant NH3 or NO2 spikes, and subsequently sick or dying fish. Daily monitoring of TAN and NO2 coupled with frequent water changes to manage NH3 and NO2 will be necessary until the biofilter cycles. Maturation of the biofilter will be indicated when TAN and NO2 have peaked and dropped, followed by a rise in NO3. Damage to a biofilter can be caused by use of antimicrobials or other chemicals and result in damage to bacteria in the biofilter. It usually takes 6 weeks for a new biofilter to become completely established. And then old tank syndrome. This is less frequently recognized. It is characterized by extremely high NH3 levels or extremely low pH, that is usually lesser than 6, and alkalinity significantly lower than what is present in source water. Inadequate water changes typically precede this condition, which is caused by an accumulation of organic acids and consequent depletion of the buffering system. Over time, the biofilter bacteria acidify the water via the nitrification process, and bicarbonates are used as a carbon source by the biofilter bacteria. As buffering capacity is depleted, pH falls and the nitrification process is disrupted, leading to a rise in TAN. Aggressive water changes will correct the situation, but neutralizing the ammonia is recommended to avoid a sudden shift of NH4 plus to NH3. The biofilter will have to be re-established and the system should be managed accordingly for about 6 weeks or until nitrifying bacteria have re-established themselves. Next, salinity as a cause of environmental disease. Seawater is a complex mixture of ions and consequently adjusting salinity in marine systems requires the use of natural seawater or an artificial sea salt product. In contrast, salinity adjusts to freshwater systems can be accomplished using simple NaCl. Table salt or water softening salt are both acceptable. Adjustments to salinity can enhance parasite control protocols and are also valuable for osmoregulatory enhancement, which may be indicated by disease or handling transport. Salinity is measured using a clinical refractometer or an expensive hydrometer or inexpensive hydrometer, the latter of which can be purchased from a pet store. Almost all water quality parameters are reported as parts per million, that is ppm, which is milligram per liter. However, salinity is reported as parts per thousand, which is gram per liter. Now, temperature is a cause of environmental disease. Environmental temperature is extremely important to the health and well-being of fish and other aquatic species. As poikilotherms, fish have a very limited ability to control body temperature, and physiologic systems are designed to work optimally at species specific temperature ranges. Sudden changes in temperature of even just a few degrees can result in compromise of immunity and increased pathogenicity of some infectious agents. Some fish are very tolerant of a wide range of environmental temperatures. However, this does not imply that drastic temperature fluctuations are acceptable even for these species. Others, such as discus, thrive in only a very narrow temperature window. When evaluating housing and husbandry, veterinarians should know the temperature at which animals are being housed and confirm that it is appropriate for the species. Suboptimal environmental temperature is an important component in some fungal infections. Microbacterium species is an important infectious pathogen of fish and other aquatic organisms. There have been many species of Mycobacterium identified in fish. However, all are non-tuberculous and most are environmental. Typically, environmental conditions common in aquaculture favor the growth of Mycobacterium. These conditions include low dissolved oxygen concentrations, accumulation of organic debris, and particularly biofilms, as well as acidic pH. Correction of these environmental factors can also enhance efforts to control the disease. Mycobacteria are hydrophobic because of their thick, waxy cell walls and tend to adhere to the surfaces and each other. Once infected fish are present in a system, these animals may continually shed the organism in feces and cells released from external lesions. Ultraviolet light, which may help decrease transmission. Bacterial gill disease as an environmental consideration of aquatic systems. Bacterial gill disease is an important disease of cultured salmonids and has been reported in other species also, including hybrid striped bass. It is rare in aquarium fish. It is caused by bacteria in the genus Flavobacterium and other closely related genera and is manifested by gill pathology and subsequent mortality also. However, bacterial Gill disease has an important environmental component and mechanical damage to gill epithelium, which may be caused by excessive crowding and debris in the water column, is believed to be an important predisposing factor. Cleaning the environment, removing debris, and decreasing stocking density all contribute to a positive treatment outcome. Correcting these underlying problems also prevents recurrence of the condition. Now let us see about the aquatic pollution. So what is pollution? The presence of unwanted substances in excess amount, that is more than required, is called a pollution. So if they are present in water, it is called as water pollution or aquatic pollution. So what are the causes of this pollution? It can be common wastes. Now, some of the common wastes that cause aquatic pollution are wastewaters, domestic waste, urban runoff, industrial wastes, pulping waste, and petroleum refinery waste, food processing waste, mining waste, etc. So, most of these wastes enter water bodies in partially or untreated condition. They cause the aquatic pollution. Not only common waste, the runoff from the fertilizer industry also. Some of the aquatic pollution problems are created with fertilizers and their excess use, which is carried as runoff, which will enrich the nutrients of water bodies. They enter, resulting in more growth of algae and other organisms. Then, power plants also. Power plants mainly use coal for the generation of electricity, will release various kinds of byproducts such as bottom ash, boiler slag, and fly ash. So, biologically toxic elements present in these waste can alter chemical and biological characteristics of soil and water. So, they will have adverse effects on aquatic life. Not only these, even the detergent manufacturing industries also. So, a number of industries release discharges contaminated with phosphates, which in higher concentration can damage the gills of fish inhabited in such waters. Similarly, pollution problems are created with phenolic compounds used in various pesticides, biocides, and herbicides. Normally, these are composed of organochlorides like DDT, indane, etc., and organophosphates like malathion, parathion, then carbamates, example garbaril, and herbicides like diquat 2,4-D, etc. So these compounds, when discharged regularly into water bodies, will get accumulated in fish and other organisms and cause death. There are some heavy metals and radioactive substances also. Pollution problems caused by heavy metals and radioactive substances are detrimental to the aquatic life, especially fishes. Effect of pollution on aquatic organisms or acute toxicity causing mortality. Sublethal behavioral effects, measurable biochemical changes, sublethal impairment of various aspects of physiology and morphology, and chronically accumulating damage, ultimately causing the death of the fish. Even the poorly managed fish culture ponds also leads to the death of the fish. In intensive fish culture ponds, care must be taken to ensure adequate water exchange for maintaining water quality in terms of supply of oxygen, reduced carbon dioxide, reduced ammonia, and suspended solids. Fish farms are particularly vulnerable to the effects of pollutants entering the water, usually from agricultural or industrial processes. These can cause reduced performance or sudden mass mortalities of fish known as fish kills. So there are so many types of pollutions like natural pollution, agricultural pollution, municipal pollution, mining pollution, industrial pollution. Then we also can study the effects of this pollution on the fish. The osmotic pressure is increased, then change in pH beyond the limit of tolerance, coal ash pulp, etc., they cause damage to the fish. Even the food of the fish also gets affected by the pollution. And sometimes pollution may come in the way of migration of fishes also. So there are now we can also call it distillery waste also. This is another kind. The origin, fermentation and distillation of corn, rye, and malt to produce whiskey, molasses, and cane syrup for rum and alcohol. So they also produce high organic waste containing much of the original solid materials in solution and suspension. Apart from these, textile wastes are there, tannery waste is there. So there are so many kinds of waste materials that damage the fish. So we'll just see the summary of this chapter. What all we have discussed. So we have discussed that water is an important component because of the physical and chemical qualities of this. They have a profound influence on pond fertility, and it also forms an ambient environment to the fishes which depend on water for their survival. So generally water is polluted from excessive release of traditional organic waste, waste generated from industries, chemical agents, fertilizers, etc. And how to take care of the fish, the and causes of pollution and consequences of pollution also we have studied. So with this, we have come to the conclusion of this lesson. Hope you all have understood. Thank you.